So we're going to be looking at applications of the tangent, more specifically using the tangent for linear approximation. Now, at this point, we may have already started noticing that when you have complicated functions, they kind of suck in trying to, figure out what the y coordinate is given the x coordinate and so on. And what a linear approximation is going to do, it's just going to give you that slightly easier equation to get close enough to the value that you're looking for in order, to continue with your life and go on with it. So in other words, use an approximation because it's a lot quicker to calculate. And even when you're doing things on your computers and such, they don't necessarily solve it exactly. They'll solve it using an approximation. Not really the linear approximation. It'll be slightly more complicated algorithms in the background of your computers programs. But the idea is approximations are often utilized to solve for values instead of solving exactly, because it's harder to solve exactly. Right. So we're going to look at the tangent line, and we just need to remember what the tangent line actually looks like. So we are well aware that the tangent slope is the derivative at that point. It's the instantaneous rate of change. So we know that it's the first derivative situation. And we're just going to quickly recap how we get the rest of the tangent line. So the rest of the tangent line is you just have to consider again your equations of straight lines. So if you think about your equations of straight lines, you'd usually have, like a y1 minus a y0 is equal to some gradient or slope. And then you have your x1 minus your x0. So that's how you would usually get that equation of your straight line. Now, in regards to the tangent, we're looking at it at a very specific point. So when we have a line, we have a point. In this case, we're going to call it x is equal to a because that's what's part of our problem over there. So then we have, the f at a as well for our y coordinate. So we have one set of points, which is this, a and the f of a. And we want to get the equation of the line. So the other set of points are the ones that are going to, be the unknowns in a way kind of a situation. They're the ones that are going to stay as y and x. So what we're going to do is we're going to replace our x0 with this a and fa and the y0. And then we're just going to rewrite this. This is your y and this is your x to get your equation for your straight line. So it's going to be any point, chilling over there or over there is going to represent your x and your y. So it's going to be the one that can be any point. Meanwhile, our set point is that point where the tangent is. It's that x equal to a and that y point with that x equal to a. So let's just rub this out. Okay, and if you rewrite it, we have y is equal to, well, let's first do all the steps. Y is equal, once more, all the steps, Trisha. Okay, y minus f of a is equal to the gradient. And the gradient in this case, we know it's our first derivative, so it's f prime at a, x minus a, and then we just make y the subject of the formula. So we bring this to the other side, and we get that equation for the tangent line. Now, because we know it's an approximation for the function we're looking at, and we utilize, the function everywhere here, we actually refer to it as L of x, the linear approximation at x is equal to your fa as f prime a, x minus a. So we can put in our x value and we'll get the approximate y value out of it. Okay, and that's the equation that you need when you're looking at the linear approximations. It's basically utilizing the tangent line and the points of the tangent line. So that you have your slope, you have your a values, and then you just substitute in your x value and you get the approximate value of y. Now, just take note that it is an approximate value, and what's going to happen is, particularly when you're going through all this process, say you have a function like that and your tangent is chilling over there kind of thing. Okay, I know that there is space in between, but I'm just trying to show to you kind of an aspect. The further away you get from where the tangent is actually, touching that point, again, pretend it touches, the less accurate this approximation is. So if you look over here, there's quite a distance between them. So the y value is going to be rather off, and it's just going to get bigger of difference. It's going to be a bigger source of error occurring there. So one of the things just to take note of, the linear approximation, or utilizing the tangent line for the linear approximation, only works really, really close to the point that you're taking the tangent at. So you have to take that into account, and you have to acknowledge it when you're doing all your calculations. So let's go ahead and do an example so you can see how you can plug the things into the equation and solve. So we have here, determine the linear approximation of the function equals to the cube root of x at x equal to 8. So the first thing you're going to do when it comes to the linear approximations is, well, let's first just remember you have the formula, right? The formula is Lx is equal to fa plus f prime a x minus a. So the first thing you have to know is, where are you taking your tangent at? So what are you going, to be approximating around? In this case, it's at x equal to 8. So your a is equal to 8. Then you also need to have a situation of, you have the first derivative that you need. So you need to solve for the first derivative. So you say, okay, well, the function of x is equal to the cube root of x, which is also equal to x 1 upon 3. Now you take the first derivative of this. So that's 1 upon 3 x, and that's 1 upon 3 minus 1, which gives you 1 upon 3 x minus 2 upon 3. All right? Okay, so you have the first derivative. But now you need to have that at that a is equal to 8. So let's just change the color for a second. So now we're going to introduce that a is equal to 8 into our working out, so we can get what our fa is. And that is just 8 to the power 1 upon 3, which is equal to 2. And we have f prime a, which is equal to, this 1 upon 3. And I've left out a step here, just by the way. I should actually be saying, that's 8 and that's 8, but I'm just discussing it with you and explaining it with you. That's why it was with the a, just to connect it. Right, so we have 1 upon 3, 8 minus 2 upon 3, which gives us 1 upon 3, 1 upon 4, which is 1 upon 12. So now we have everything we need to just substitute into the original formula. So you say, okay, well, we have L of x is equal to f at 8 plus f prime at 8, x minus 8. And we just put in all our values now. So you have 2 plus 1 upon 12, x minus 8. And now what we can do is we can just simplify it to make it look more like the standard straight line notation. So that's just 2 plus 1 upon 12x minus 8 upon 12, which gives us 1 upon 12x. And we have, okay, that's 24 upon 12. I've just taken the 2 and written it in terms of 12 just to make the common denominator, to make our lives easier, minus 8 upon 12. And 24 minus 8 gives us 16. So we end up having 1 upon 12x plus 16 upon 12. And that gives us, our approximation at the point x equal to 8. Now we can literally go and say, oh, well, what is, the y value at x equal to 7? And we can put 7 into this equation over here and solve for it. And that's what we're going to do next. We're going to do two versions. We're going to do a number very close to 8 and a number far away from 8, so that we can investigate and see, how accurate it is by looking at it, by actually solving for the function and looking at the graph, so we can just get that more clarity regarding the fact that the linear approximation is only useful really, really close to where we're taking that linear approximation. In other words, where we're taking that tangent line. Right, so we're going to use and look at the function at 8.05 and the function at 25 for this. So again, we have that Lx is equal to 1 upon 12 x plus 16 upon 12. And we're going to plug in 8.05, 1 upon 12, 8.05, plus 16 upon 12. And if we go ahead and solve for that, let me just get my calculator. .05 plus, okay, we're going to get 2.004, etc. Now let's actually solve for the function itself. So if we look at the function at 8.05, we're going to take the cube root of 8.05. So we're going to type in 8.05 to the power of 1 upon 3, or we're going to use the cube root sign, whichever one is better for you and the calculator that you are using. Okay. And it is 2.0041, etc. So those are like pretty close to each other. Overall, the approximation, is working for the function itself. Now let's solve for the function at 25 and the approximation at 25. So we're going to put in L25 equal to 1 upon 12, 25 plus 16 upon 12. Okay, so let's go ahead and type that into our calculators. 1 upon 12, 25 plus 16 divided by 12. And that's going to give us 3.416. And the 6 continues for a bit and then becomes 7 kind of a situation. It's reoccurring, 3.41. And now let's look at the function at 25. So it's the cube root of 25. What is that going to give us? So we're going to say 25 cube root and that gives us 2.92, 2.924, etc. So you can see the difference here is quite drastic in, wow, my handwriting sucks. Let's just redo that. 2.9240, etc. So you can see there's quite a large difference at the 25, because 25 is pretty far away from the 8, where we took our linear approximation. And just to give you some more clarity on this, we're going to actually look at the plotted graph so you can see it visually. So if you look there, here you have, the function at 8.05 and the tangent with the 8.05. You can actually see like that's actually, it's pretty close together kind of situation. It's accurately representing, the y value. Whereas here you have the function at the 25 and the linear approximation at 25. And you can see the further away it gets from that 8 point, the 8 point is chilling somewhere over here, the error becomes bigger. So you can see it's relatively small there. It gets bigger and bigger overall. So a thing to remember when it comes to linear approximation, the further away you are from where you did that linear approximation, in other words, where you took that tangent line, the less accurate your approximation is going to be. So that's just something to remember and to consider when you're doing all your calculations. But otherwise, it's relatively straightforward to get your linear approximation. You just need the first derivative at the point that you're taking the tangent, you need the function at the tangent, and then you put it into your equation. So let's do one more example on this. And it's a very popular example that you would have seen at school or utilized in school, where you would have said, hey, really close to theta is equal to 0. Your sine theta is approximately just the theta value itself. And we're going to do the linear approximation to show you that. So we're actually going to come out with this situation, this approximation that you would have probably used at school. And that was if theta is close to the 0 value. So let's go ahead and do that. So remember, for our linear approximations, we have the line Lx is equal to fa plus f prime a, x minus a. In this case, we don't have x, we actually have theta, so just replace your x with the theta. Okay, so there you go. And now we need, firstly, what is a in this case? A is where theta is equal to 0. So now we need to solve for f0 and f prime 0. So we first need f prime. So f prime of theta is equal to, and in this case, it is cos theta. Okay. And then cos 0 is just 0. Well, lies. Cos 0 is 1. Right? And your sine 0 is 0. Remember that your function of theta is equal to sine theta. So now we can put it into our approximation. So we have 0 plus 1, theta minus 0. So we have 0 plus theta. So we have theta. So that's where we get that situation of sine theta is approximately equal to theta when it's really, really close to theta is equal to 0. And you can see it, in that region over there. So linear approximations, you need to know the equation of the tangent line and then use the equation of the tangent line. And make sure that you are getting that tangent line as close as possible to the point that you want to approximate.